Folks, here's section 10.5, graphs of the trigonometric functions. We're going to have two different guided notes pages for this section, so I've labeled them part 1 and part 2. We also may have a couple extra examples that I put videos up in YouTube for. So I want to start with a quick summary of where we've been and where we're going with trig functions. So we started with the circular functions, and those are all the things we memorized on the unit circle. The format was cosine theta equals x and sine theta equals y. Theta was our central angle on the unit circle, and the output of each of those functions was either the x or the y coordinate of a point on the unit circle. Hopefully you recall in our discussions about circular functions that if we have an angle theta and we draw it with the initial side and standard position and the terminal side here, the angle theta has both a cosine ratio and a sine ratio. And we can have positive angles and we can go multiple revolutions. We can have negative angles and go negative revolutions, and we still get an output to the function. And that output for any point on the unit circle changes. Okay, so those are the circular trig functions. So moving from circular functions into trig functions, how are they different? Well, they're certainly closely related. The format of the trig functions is the function f of x equals cosine of x, where x is an angle measured in radian, just like theta was back over here with the circular functions. But now the output of our function is a y coordinate. So we can graph both y equals cosine of x and y equals sine of x on the same set of axes. X is our input or angle measure, and then y is the output of each of those functions. I'll go ahead and quickly graph one period of both cosine and sine for you. These graphs should be very familiar to you. Cosine starts at 0, 1, then has a point at pi over 4, root 2 over 2, pi over 2, 0, 3 pi over 4, negative root 2 over 2, and then pi, negative 1. And then we climb back up until we get right back where we started at 2 pi with an output of 1. So that's the graph of y equals cosine of x. Y equals sine of x looks pretty similar, except we have a little bit different starting point. And I know I'm going through picking these points very quickly. I'm assuming that, and I know what they say about assumptions, those aren't always the wisest thing to do, but I'm assuming that you can repeat those graphs as needed, especially those basic ones. Okay, now I know you've seen these graphs before, but there are a couple things I want to point out. First of all, the graphs are identical with the lone exception of a horizontal shift. And hopefully you recall from a previous lesson, the cosine of theta is equal to the sine of its complement, or pi over 2 minus theta. So because of that relationship right there, these two graphs are equivalent other than a horizontal shift. The other thing I'd like to point out here is that the cosine graph starts at 0, 1, and the sine graph starts at 0, 0. That's just a little reminder for you of where these graphs start if you have to graph them by hand. Okay, so speaking of graphing by hand, what a pain that is to do. So it's great to have graphing calculators and computers that do that for us, but I think it might be worth the time and the exercise to just do one by hand so that we really appreciate what our computer and our calculators can do for us. So we're going to go ahead and graph this one by hand. F of x equals 2 times the sine of pi minus 2x all minus 1. And the procedure for graphing a trig function that has a couple different transformations in it is kind of tedious. I've outlined it here as a 4-step process. Each of these steps you need to do for each of the quadrantal angles. So you need to do it for an angle of 0, an angle of pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to go ahead and do the first one kind of slowly for you, and then I'll go through the other ones pretty quickly. All right, step 1 says, set the argument of the trig portion of f of x equal to the quadrantal angle on the unit circle. Well, here's the argument of the trig function. It's that thing that's inside the parentheses. So I need to set that pi minus 2x equal to my quadrantal angle of 0. So solving this equation for x gives me x equals pi over 2. Add 2x to both sides and divide by 2. Okay, step 1 is done. Step 2, evaluate the trig part of the function. So I'm going to plug this x value, pi over 2, into this expression. That's going to give me the sine of pi minus 2 times pi over 2. That turns into the sine of pi minus pi, or the sine of 0. And the sine of 0 is 0. So we're done with step 2. Step 3 is to evaluate the remaining part of the function. So I'm going to basically do all the multiplication, addition, subtraction for each of these pieces. So I have y equals 2 times the sine of pi minus 2x. We just did that in the previous column. That's 0. And then minus 1. 2 times 0 minus 1 is negative 1. So I have an x-coordinate of pi over 2, and I have a y-coordinate of negative 1 on the graph of this function. So let's go ahead, now that we're done with step 2, let's go ahead and graph that ordered pair. Pi over 2, comma, negative 1. Pi over 2, comma, negative 1. So that's a point right there on the graph of the function. Okay, so what I'd like you to do now, folks, is I'd like you to work through the rest of these quadrantal angles and see what the rest of the graph looks like. I'm going to go ahead and pause the video and work through the rest of this table. I want you to do the same thing and then check your answers with what I get. Okay, folks, I have gone ahead and completed the table. Hopefully your table matches up with mine, and then I graphed each ordered pair and I get a plot that looks like this. At this point I would probably sketch a smooth curve through those points, and what I'm left with is one period of the graph of 2 times the sine of the quantity pi minus 2x, all minus 1. Okay, congratulations, you finished side 1 of the notes. We're now going to move on to side 2. For side 2, I'm going to go ahead and talk about just this first box, and then probably shut it down because we're getting close to the 10-minute point, and start a new video. So what we're doing here is we're talking about transformations of sine and cosine for omega. Omega, that's the Greek letter omega, this guy right here. For omega greater than 0, and we'll always want to force omega to be greater than 0, and we'll see a couple examples of that later. So I have two crazy looking functions here. One of them says capital C of x equals a times the cosine of omega x plus phi, all plus b, and then I have the sine equivalent of the same thing. Well, before I go and talk in much detail about what all the different pieces, parts of this mean, let's take a look at this graph. So the periodic sine and cosine functions, they're wave functions. They increase, then they decrease, and then they increase back to where they started. So they have that oscillating behavior, and we have some definitions that define that oscillation. The first thing we have is amplitude. Amplitude is the distance from the baseline to the peak of the graph. It's also the distance from the baseline to the minimum of the graph. So the way that we can find that amplitude value is as follows. Amplitude, which will always be reported as it's a distance. Okay, so it's a distance, so it'll always be reported as a positive value, and amplitude is going to be max minus min divided by 2. Max minus min, and when I say max, I mean the max there, and min is the minimum there. So max minus min divided by 2 will give you amplitude. Next thing we'll talk about is the baseline. Okay, and the baseline is the midpoint of the function, and that is the average of the max and the min. And the way we find an average of two numbers is we add them and divide by 2. So our vertical shift B is going to be max plus min divided by 2. Now, these two formulas, they look really similar. They only differ by a sign there. One is subtraction, one's addition. So it's on you to try and find a way to come up and remember the difference between those two. For me personally, I like to think of, the distance from here to here. This vertical change is top minus bottom, max minus min. If I want to know half of that, I divide by 2. That's how I get amplitude. Vertical shift, or the baseline, the location of the baseline, it's the average of the max and the min. It's directly between the two. Okay, the next definition we'll talk about here is period. And the period of a function is the length that it takes to go one complete cycle. Okay, and that's called the period. Okay, so the period of the sine and cosine functions is calculated as 2 pi divided by omega, where omega is something called angular frequency. I better write that down. You might want to know that later. Omega is angular frequency. And that's a lowercase Greek letter, omega, angular frequency. Phase is something called phi. Phase shift is negative phi divided by omega. I'm actually going to show you a different version of each of these functions. C of x equals a, or amplitude, times the cosine of, and I'm going to factor out an omega. From inside the parentheses there. When I factor out an omega there, I get omega as a multiplier, and then I get x plus phi over omega. Well, phi is the phase shift. It basically describes the horizontal shift left or right of our function, and that phase shift is the opposite of phi over omega. And in a second here, I'm going to show you how that actually connects to some things we've done before with transformations of functions. I can do the same thing here with sine of x. A times the sine of omega, I'm going to factor that out, times x plus phi over omega, all plus b. So those two forms, I prefer this second form, but you're going to see it both ways, so I'm showing you both ways. Last thing I want to show you here is I'm going to go ahead and erase this term angular frequency here, because I got something I want to pull out and show you. Do you remember this? This is the general form of a function transformation. G of x is a transformed function of f if I multiply a times f of the quantity bx plus h, all plus k. A, b, h, and k are all parameters that affect the transformation of f to g. I want to show you a quick example of this and how it relates to the trig function, so hold on just a second. What I have prepared for you folks is a quick little demonstration in Geogebra how each of these different parameters, a, b, h, and k, affect the graph of our friends, the trig functions. So there's our standard cosine, y equals cosine of x. A, if you recall, any coefficient out here is a vertical stretch. We now call that amplitude. B is a horizontal stretch. That's now related to frequency. It's also going to be something that it affects the period or the length of each wave in our trig function. H was horizontal shift, left or right. That'll be what we call phase shift. And last but not least, K is our vertical shift. We can move our baseline up or down. Okay, we can do the same thing. We can see those same transformations if I turn on the sine function. Shift left. Oh, that looks kind of cool. Okay, pretty exciting stuff here, folks. So the reason why I put this together is just to show you that everything we're going to look at now with the transformation of trig functions it's all stuff we've talked about before. We're now just applying it to a new type of function, our trigonometric functions. Okay, folks, I think I want to kind of wrap up this video before I get into examples 3, 4, and 5, because those are going to take quite a while. So apologize for the length of this video. You're going to see in the next 3 examples how all this stuff relates to the graph of the function.